unless some voltage there, maybe it will not conduct. So current is not there in quotient state, and increases with excitation. As you increase the excitation at the base, power consumption increases. Whereas the heating of the collectors of the class A system is a maximum at zero input and decreases as the signal increases. Okay, if we take this inside, then that will happen. Since the direct current increases with signal in a class B amplifier, the power supply must be good regulated. I mean, nicely regulation. There should not be any ripple or that kind of things. The collector dissipation PC in both transistors is the difference between power input to the collector circuit and the power delivered to the load. Since I am the maximum or peak value of current, Bm by RL prime, the PC equals to Pi minus P equals to, putting the values of Pi and P, we get this expression. This equation shows that the current dissipation is zero at no signal, that is Bm equals to 0. Rises as Bm increases and passes through a maximum at Bm equals to 2 VCC by pi. The peak dissipation is found to be PC max equals to 2 VCC square by pi square RL prime. The maximum power which can be delivered to obtain is obtained for Bm equals to VCC. If B min equals to 0 or P max equals to VCC square by 2 RL prime. Hence, PC max will be equal to, putting the values, almost equal to 0.4 P max. If, for example, we wish to deliver 10 watt from a class B push-pull amplifier, then PC max equals to 4 watt. Or we must select transistors which have collector dissipations of approximately 2 watt each. In other words, we can obtain a push-pull output of 5 times the specified power dissipation of a single transistor. On the other hand, if we paralleled 2 transistors and operated them class A to obtain 10 watt out, the collector dissipation of each transistor would have to be at least 10 watt, assuming 50% efficiency, of course. This statement follows from the fact that Pi equals to P0 by eta, where eta is the efficiency, which is taken as 0.5. So 10 by 0.5 equals to 20 watt is the value of Pi. This input power must all be dissipated in the 2 collectors at no signal, or PC equals to 10 watt per transistor. Hence, at no excitation, there would be a steady loss of 10 watt in each transistor, whereas in class B, the standby, no signal or quotient state, dissipation is 0. This example clearly indicates the superiority of push-pull over the parallel configuration. Now distortions, we are going to start. The output of a push-pull system always possesses mirror symmetry that we have discussed earlier, so that IC equals to 0, Imax equals to minus I min, and I half equals to minus I minus half. Under these circumstances, equation 18-18 reduces to B0 equals to B2 equals to B4 equals to 0, and B1 equals to 2/3, within parenthesis Imax plus I half, and V3 equals to 1/3 Imax minus 2 I half. This equation we have already seen, equation number 18-18, and those constants B0 to B4 can be written in this way. Note that there is no even harmonic distortion that we have already analyzed and understood. There will be no even harmonic, only harmonic will be the odd. The contribution to principal contribution to distortion is the third harmonic, given by D3 equals to mod of B3 by mod of B1. The values of Imax and I half are found as follows. A load line corresponding to RL prime equals to N1 by N2 whole square into RL. This equation we have discussed earlier is drawn on the collector characteristics through the point IC equals to 0 and VC equals to VCC. I mean load line. Talking about the load line, you see that. So the load line drawn for IC equals to 0. IC equals to 0. This is the point. And another point is VC equals to VCC. DC equals to VCC. So these 2 points, and it is drawn, the load line is drawn. If the peak base current is IB the peak base current, then the intersection of the load line with IB gives the Imax here. And with the IB by 2, I mean, if maximum value is divided by 2, the characteristic I half is obtained here. The power output taking distortion into account will be E equals to 1 plus D3 square within parenthesis and B1 square RL prime by 2. Now a special circuit. We're going to talk about this special circuit where we can eliminate the output transformer, or even we'll see later on that input transformer is also can be eliminated. This one also can be eliminated later on. A class B configuration of which dispenses, I mean not uses, with the output transformer is shown here. This arrangement requires a power supply whose center tap is grounded. The center tap has to be grounded as center point has been grounded. Power supply is such, the power supply is such that its center point is grounded here as shown here. This is the condition to replace a output transformer. A circuit that requires neither an output transformer here somewhere and an input transformer in this side. So both transformer, input transformer and output transformer are eliminated. So what is the requirement? The requirement is that a PNP and NPN complementary transistors should be used. Okay, this arrangement is transistors having complementary symmetry, that is one PNP, one NPN. The difficulty with the circuit is that of obtaining matched transistors. These two transistors, NPN and PNP, should be matched. I mean, its output characteristics should be balanced or matched. If there is an unbalance in the characteristic of the two transistors, considerable distortion will be introduced. Even harmonics will no longer be cancelled. A very negative, very open, a negative feedback is used in power amplifiers to reduce nonlinear distortion. So using this kind of transformer-less amplifier is possible only when if it is available. I mean, PNP and NPN matched PNP and NPN are available. Now crossover distortion, what is that? We'll discuss now. In addition to the distortion introduced by not using matched transistors, and that due to non-linearity of the characteristics, there is one more source of distortion that caused by the non-linearity of the input characteristics. As pointed out earlier, no appreciable base current flows until the emitter junction, base emitter junction is forward biased by the cut-in voltage, which is zero point 0.5 for silicon. Mostly silicon devices are used, so let us stick to this value. Of course, germanium is having the value of 0.1, gamma V gamma equals to 0.1, but we will talk about 0.5 volt in case of silicon because mostly silicon transistors are used. Under these circumstances, sinusoidal base voltage excitation will not result in sinusoidal output current. I mean, collector current will not be there because until unless your input is crossing some value of 0.5 volt, no base current is there. If base current is IB equals to 0, then you don't have the collector current because IC equals to what? In general, you know, IC equals to beta IB or not? Yes or no, Pratham?
Yes, sir, beta IB.
So cutting voltage till cutting voltage is crossing input signal. Suppose you have biased in such a way that it is I mean base voltage is 0, and you are applying a input signal at the base. Until it is crossing this 0.5 volt cutting voltage, no current IB is there, so no IC is there. That's the concept. So let us see what is further written about this. This is the cut-in voltage. Cut-in voltage 0.5 volt in case of silicon. The distortion caused by the nonlinear transistor input characteristic is shown here. The IB VB curve for each transistor is drawn and the construction used to obtain the output current. In the region of small currents, that is VB less than V gamma, the output is much smaller than it would be if the response were linear. See here, till this point you don't have IB. After that, it's a kind of diode characteristic. Are you seeing this one? Diode you have seen. You'll see the diode characteristic also like this. Until its cutting voltage is or 0.7 volt is crossing, appreciable current will not be there. Of course, if you expand this portion, you will get little current, but it is very negligible. This effect is called the crossover distortion. Corresponding to this IB or say VB less than V gamma, you will not have IB, so you will not have IC or collector current also. This is nothing but crossover distortion, and this you see that during the crossover there is no current, collector current. I mean, one transistor is off here at this point, but other one is not on immediately. Are you getting my point? Here, say one transistor is say push-pull connection. You think of where two transistors are there. See, one is on, other is one is off. This side is off, left side is off. This side is not yet on. That is happening. Okay. This will be more clear with this diagram. Crossover distortion is occurring here during the switching off. One is off, another is on. Crossover distortion produces a zero voltage or flat spot or dead band on the output wave shape as it crosses over from one half of the waveform to the another. This reason for the reason for this is that the transistor period, when the transition period, when the transistors are switching over from one to the other, does not stop or start exactly at the same time. See, it is the status of V in up to this point. Here 0.7 volt is shown as cutting voltage. In Willman, Halkias, it is giving 0.5 volt. Doesn't matter. point is here that up to this value of voltage, input voltage, that is VV, VVE, there is no conduction. I mean, IC will not be there because IB is not there. Okay, so crossover will go to occur. Okay, could you understand what is crossover? Pratham?
Yes, sir.
Okay. This type of, see, this crossover can be eliminated by using a register, voltage divider kind of register. Okay, as is VCC is tapped here, and some voltage is available. I mean, at the base, that may be equivalent to or equal to cutting voltage. Okay, 0.5 volt or so. So that even when your input signal VV is 0, still it is conducting. Okay, still it is conducting little current. Okay, so this type of resistor pre-biasing causes one transistor to turn on exactly at the same time as the other transistor is turned off. Okay, as both transistors are now biased slightly above their original cutoff point. This pre-biasing can also be implemented in transformer-less. There was a transformer here. It can be transformer-less also. Only thing you have to use resistor as well as diode. Okay, resistor as well as diode. Okay, diode biasing. To minimize crossover distortion, the transistors must operate in class AB mode. What is the conduction angle of class AB? At least remember this thing.
Greater than
Great.
180,
But less than 360.
Good. So it should be operated at class AB, where a small standby current flows at zero excitation. Excitation means your BS is 0. Okay, BS is having your sinusoidal form. For example, at 0, BS equals to 0. Here also excitation in the secondary is 0. No base voltage is arriving here, that is positive or negative. But you have biased in such a way that the base voltage is greater than current voltage. Okay. So the transistors must operate in a class AB mode where a small standby current flows at zero excitation. In the circuit shown here, the voltage drop across R2 is adjusted to be approximately equal to V gamma. This is cutting voltage. The class AB operation results in less distortion than class B, but the price which must be paid for this improvement is a loss in efficiency and wastage of standby power. That is obvious. It is when signal is 0, input signal is 0, still it is conducting because of the this kind of biasing, because we have applied base voltage which is greater than 0, around 0.5 volt or 0.7 volt, which is cut-in voltage. Understood? So, loss of efficiency and wastage of standby power. Okay. Now, class C amplifier, we are going to start. Class B is over. Class B is over. Now we are starting class C amplifier. We little talked about class AB, I mean, in this discussion. Now we'll concentrate on class C amplifier. Here the diagram shows the class C output stage, where one RFC is there at the collector of the transistor, NPN transistor. RFC, radio frequency coil. is used here. So we have seen that the class A power amplifier is biased in active region to produce a linear output signal with minimal distortion. However, due to this biasing arrangement, the transistor remains on even for non-input, no input signal, means when VB0, or you can say if you consider the source voltage VH is 0. However, due to this biasing arrangement, the transistor remains on. Okay, this results in a poor efficiency of the class A power amplifier. Efficiency is around 50%. In order to improve efficiency, the class C power amplifier is used. In the class C amplifier, the transistor is biased such that it remains off for no signal conditions and operates in the saturation region when an input signal is applied. When the transistor is off, the current through it is very small and hence the transistor dissipates negligible power. Okay. Similarly, when the transistor operates in saturation, the voltage across it is very small. See, saturation voltage of a transistor is denoted by VCE. What is the value? Can anybody say? You have studied earlier also.
0.2.
0.2 volt.
Yes, very good. You are remembering. So the statement here is telling that when the transistor operates in the saturation region, the voltage across it is very small. And again, the power dissipation is going to be small. Voltage is less, so power dissipation is also going to be small. Therefore, in the class C amplifier and the transistor dissipates less power, its efficiency is higher than that of the class A amplifier. However, the class A amplifier is highly nonlinear, produces distorted output. This drawback of class C amplifier is overcome by connecting a low pass filter. Here you have connected a low pass filter to overcome this problem. Distortion is very high, harmonic is there, so that has to be suppressed. For that, a low pass filter is used here. LC, low pass filter, is used. This low pass filter blocks all the high frequency harmonics and passes only the signal frequency to the load. Load is antenna denoted here because the power amplifier in a transceiver, the load is nothing but your antenna, which is having a characteristic impedance of 50 ohm. The schematic diagram of a class C amplifier is shown here at the bottom. While, see, are you taking the snapshot of this or not? Everything is not from Milvan Halkias. This is from Shedra Smith. This diagram, class C amplifier, is taken from there. So take this snapshot and read it later on. While the input and the output waveforms are shown here in this. Okay. This is input waveform applied here at the base of U, and the output waveform at the collector of the transistor. When the input signal is positive, this cycle positive and above the cut-in voltage of the transistor operates in saturation. Once it is saturation, see, which is at say around 0.2 volt will be the value here. During this period, the output voltage is equal to the saturation voltage of the transistor and remains constant as long as the input signal is above the cut-in voltage, that is V gamma. When the input voltage is less than the cut-in voltage, means negative excursion of the input signal, this one, the transistor remains off. So during positive excursion, transistor is on and it is in saturation region. So voltage across the collector to emitter is nothing but 0.2 volt. It is on. When it is negative, input signal is negative, it is off. Okay. When the input voltage is less than cut-in voltage, the transistor is off, while the induced EMF in the inductor provides the collector voltage. Collector voltage there. See, collector voltage is shown here at the output, and that is given by supplied by inductor, where the induced EMF is there. Okay. This output voltage fed to the low pass filter. The low pass filter suppresses high frequency harmonics present at the collector and produces output similar to the input signal. Okay. Efficiency of class C amplifier, power efficiency, of course. So for that, the circuit, class C amplifier circuit is modeled as shown here. VCC is given here, RFC, and the coil, radio frequency coil, and the transistor is sometimes on and sometimes off, so it is represented by the switch. Okay, and this is the 0.2 volt saturation voltage. Okay, in off state it is it's in off state. On state it is 0.2 volt. On state it is 0.2 volt. When it is on, then 0.2 volt across it, and when it's off, then the voltage is supplied to the load through the filter by this RFC. So to derive an analytical expression for the power conversion efficiency, the class C amplifier is modeled as shown here, and the corresponding output waveform is shown in this diagram. According to the model shown, the collector voltage when the transistor is off, the switch is open, is given by Vc of t equals to Vc sat plus Vm cos omega t. Okay. And when the transistor is on, the switch is closed, and Vc E of t equals to Vc sat 0.2 volt only. That will be 0.2 volt. However, in the class C amplifier, the time average value of DC of t must be 0, as the DC resistance of the coil used is approximately 0. Hence, we can write this expression as A as VC sat is very small as compared to Vm. As compared to Vm, the above expression can be modified as follows: VCC equals to VC sat plus 1 upon t, and integration of Vc of t is the period from 0 to t by 2 equals to this, putting the value of this. So we get this expression here, VCC equals to VC sat plus Vm by pi, where Vm equals to pi into VCC minus VC sat. The DC power supplied is given by EDC equals to VCC into IDC, where IDC is the average value of supply current. Due to the blocking capacitor, the same average current flows through the transistor when it is in saturation. The power dissipated is given by PT equals to BC sat into IDC. The remaining power must appear as useful AC power across the load. Hence, the AC output power is given by PAC equals to PDC minus PT. PT which is dissipated. So we get this expression, putting the values, and hence PAC can be written as this. It is common taken and written this way. Hence, the efficiency of the class amplifier eta can be written as only 1 minus VC sat by VCC. Since VC sat is very small, say 0.2 volt, and this is say 5 volt, so efficiency is very high. As you can see, it can go up to even 90%. So with this, your first module is over. Now we'll have to conduct the quiz. So you decide a date and tell. Pratham,
Yes, sir.
decide a date. Now you discuss among yourself and tell us. You can give 1 or 2 alternative date and time. Somebody propose a date and time. Others will say yes or no. So your lab will start also very soon. Remember, whichever lab is not done in the last semester, that will be started first. Okay. So you cannot just keep things pending. Yes.
Sir, next Thursday. The next Thursday.
Next Thursday. What others say? What about others?
Yes, sir. We are also comfortable.
Today is Thursday. You are telling next Thursday. Timing?
Sir, class timing only.
Means in this class timing you want to finish it up.
Yes, sir.
Okay, class timing. Okay. Okay, any alternative date if you want? Suppose other section is also there, na? Think of other time, others also. They may or may not agree. So that's why I am telling you, give an alternative date. Tell some other alternative date. What is the date?
It is possible on Thursday.
Friday.
We can do it on Friday.
What you said? Friday, Thursday, otherwise Friday.
Next Friday, 4:30.
Friday, 4:30 or Thursday class time. 11:32 onwards. 11:30 onwards. Okay, this 2 days you are proposing. 2 day and time. I will discuss with the teachers of other section, and their opinion also will be taken. Okay, and then will be taken. Let me. I think class is going on for that section also. She will be busy for class. So I'll try to contact and tell your opinion. हाँ रुपेश जी क्लास में है हो गया अच्छा ये स्टूडेंट बोल रहा था कि थर्सडे अगले थर्सडे सेम टाइम मतलब क्लास टाइम आज थर्सडे है ना सो 11:30 बोल रहा है या तो फ्राइडे 4:30 जो भी सूटेबल हो आपका स्टूडेंट्स को जरा बोल के देख लीजिएगा ठीक है अच्छा रखते हैं ओके your opinion is transferred to other teacher which will discuss with them and then we'll be finalizing right it will be based on your choice only either you from this section or from other section okay so time still there we have 12:30 onwards no so let us see what we have to 12:30 up to 12:30 we have the class so we'll see what is there in this next module so that we can have a plan. See in this module 2 we have to study these topics multi-stage amplifiers frequency response of an amplifier band pass of cascaded stages low frequency response of RC coupled amplifier transistor at high frequencies hybrid pi model and parameters high frequency response of C transistor then gain bandwidth product emitter follower FET based FET means MOSFET based CS and CD amplifier common source and common drain at high frequencies tuned amplifiers will be discussed in the next this module 2 okay so we'll stop here or continue yes if you want I can stop if you want I can continue
So we can start in next class.
okay so every day I'm taking less more time let us finish today a little early enjoy leave the class and attend other classes